talk in the classes that I taught when I taught operating systems class. I've always found that knowing how to effectively debug programs is a really hard thing to teach for a fairly simple reason. At the point at which you really need this information when you're a freshman and you're starting out, wouldn't it be really handy? You're not writing any, nothing personal, you're not writing any programs big enough that it's really an interesting problem to learn the debugger, because they're only 30 lines long, how bad could it be, right? By the time you get old enough or you've been in this long enough that your programs are really complicated, then you needed the information but you haven't had it. So I usually try to sprinkle this stuff around a little bit. I'm going to call this Unix debugging at Ohio University. It's a talk about GDB. There are lots of debuggers out there and they have lots of stuff in common. I'm primarily going to talk about GDB stuff. I'm going to do a lot of examples, I hope. It would be more helpful if you guys would ask questions, interrupt. XKCD, sure. What else is on there?
Oh, it's me.
All right. Making a sandwich. All right. Okay, so I'm going to talk a little bit about how you prepare a program for debugging. I'm going to talk about the GNU debugging program in particular. I'm going to talk about several different interfaces it has. I've got a whole lot of examples depending on how long you guys can tolerate it. This stuff is on my website if you want to grab it off of there. The examples are not, but I suppose they could be. So let's see. Let's stop and review just a little bit so that we're all talking about the right kind of stuff. So I assume you guys are all using some standard compiler. We'll pretend we're using GCC for now. So when I use something like this, and I say GCC minus C x1.c, what does that do?
Builds an object file.
Ooh, that's a good answer. It builds an object. What in the world is an object file?
It's stuff that has code in it.
Stuff that has code in it. So it's mostly the machine language version of this stuff with a bunch of information about which subroutines are in there in case I need to use them and which subroutines it needs to call so I can go and find them later. So if you've got a program that's got a whole lot of C or C++ files, essentially what you're going to do is you're going to create a whole bunch of these object files, and then you're going to put all of those object files together through a process called
Linking.
linking, thank you, to find all the subroutines in those files that call each other, make sure they all get linked together, and then find all the missing subroutines for input and output and system calls and stuff, and bring those all in there and get one executable program. Now, if you're kind of lazy about this, the executable program you're going to get out of this is going to be a.out or something. I'll just call mine X because it's far more descriptive. So that gets us to the point where we've got a running program. So no big deal so far. Now, I need to talk a little bit about compiling options because when you're debugging, this stuff is even more important than normal. So the first one we need to talk about is -G. Now, which I suppose used to stand for use GDB. So when you build a program, if you want to be able to debug it effectively, you've got to have all kinds of information about which line from the source file is involved with each instruction, all sorts of stuff like that. So what we need is a huge bookkeeping piece. Where does this variable get stored? Where is this subroutine stored? Stuff that you really don't need to run the program, but that you do need to debug it. Now, -G will put that in. For your purposes, it's never really a problem. It will make the executable quite a bit larger. In my experience, it never makes the program slower, but it will make the file a lot larger. On the off chance you're going to need to debug it later, it doesn't hurt to put that in. So it never really hurts you. If this is a professional program and you were going to sell it or something, you wouldn't want to do this because it would be giving people a lot of information about your source code, which you might not want to do. But for the purposes of classroom and debugging things, it's fine. Now, let's see here. The standard error messages that everybody always includes, and there's a point to this, is -wall, which means, hey, GCC, complain about anything you can possibly imagine, no matter how mad it's going to make me. And -whereer, which says, hey, all those little warnings, like, I really don't like the fact you don't have a parentheses, make those all fatal. Okay, really important. Why? Well, the first step to debugging a program is not putting the bugs in the first place. I find that it's very effective. And compilers are really good about warning you about that stuff. So chances are, if I turn this on and it complains about something, you should change it. it either is an error, or could cause an error when you edit it later, or is non-standard or something. So what these do is they will make sure that whatever source code you've got, it's as clean as it can possibly be. Now the reason for that is it's really annoying to spend an hour debugging a problem the compiler told you about last night and you ignore it. All right, so don't ever do that. Now, the more important part is optimization for our purposes here. There's -O, which means optimize the program, same as -O1 generally, and that's usually the default unless something has been changed. -O0, do not optimize. We will get back to that in a little bit. Do some more, etc. So generally, when I'm compiling anything, I'm going to use -G for debugging on the off chance I put a bug in it, -wall, -where, and -O2. -O3 tends to take quite a bit longer if it's a big program. I find it isn't particularly worth the effort. One nice thing about -O2 is it will find other bugs in your program, like uninitialized variables, unused, all sorts of stuff. So it will help you find problems before you even run the program. So typically you get much better compiler warnings with this. All right? So far so good. Anybody else got any favorites they like to use? I mean, there's a whole bunch of other things you can throw in here, like pedantic, if you wanted to complain about things that used to be cool but we don't do anymore and stuff like that. But I find that's the best substitute. Okay, fine. So we got a program, we're going to debug it. Isn't that exciting? All right. There are, if you're a touch typist and you like to do things very quickly, then you probably do your debugging from the command line, or you're going to do it from another interface, and we'll talk about that in a little bit. The basic ways to start a debugging session on a program in the command line, there's two ways to do it. I can run gdb and the name of the program, or X, whatever the file was, and it will give me a prompt here, and we'll play with some examples of this in a little bit. Now, what that would mean is I want to start this program from the beginning and talk to it. On the other hand, let's say that your program dumped core. We hate when that happens. And it'll leave this file called core in whatever directory you're in. Now, the whole purpose of the core file is to take up your disk space and lay around and make John Tisco mad. But they're actually really useful. Where in the world does that name come from? You can't answer. Why do we call it a core file? All right, you can answer.
I know they used to call the memory core in the old days.
Yeah, it's core memory. Back in the ancient days when memory cores were little donuts, electrically isolated, a core file was all of the memory in the entire computer, because you only ran one program at a time. So a core file was all of the memory on the computer when something went wrong. And we've called it a core dump file ever since. So what this is now, it's not all the memory on the computer, but it's all the memory from the program that was running, along with where it was, where all the variables held, stuff like that. If the program crashed, let's say it's one of those annoying programs that runs for a week and then crashes, those are no fun to debug. If that happens, and there's information in this core dump file that will probably tell you where the program was. So if I have a core dump file, I can do this, and I can say, where are you, what's going on? And it will tell you what happened, even if it didn't just now crash. That can be really useful. I find that it's a little bit buggy, so I only use that if it's a problem that I can't easily reproduce. If it's a problem, I run the program and 2 seconds later it crashes, then this isn't very accurate. But in a pinch, if all you've got is the core dump file and you can't recreate a problem, then you can do that. Okay? Other than that, the core dump files don't do you much good. Okay, so I'm going to, well, let's see, we'll switch to an example here in just a little bit. So to run a program, you're going to get a prompt, and I'll show you the prompt in a minute. If I switch back and forth, it'll make my machine mad. I'll say run inside GDB, and it will run the program. If your program has arguments, you can say run -f, this file, that file, -a, foo, bob, whatever you've got in there, whatever the command line arguments are, you type run, and it will run your program just as if you had run it from the command line. But underneath it will be this GDB debugger keeping an eye on it and sort of babysitting to see what happens, which is really useful. One thing that's handy is that GDB was written by real geeks who want to do things very quickly. It's got hundreds of optimizations and shortcuts and helpful things. So let's say that your program has 10 arguments and you don't want to type them in every time. If I just say run, it will keep using those same arguments. So it can make things kind of nice. if your program always crashes, dumps core, gets some sort of an error, then I can just type run, wait for it to die, and then see what happens. Now, a lot of times, I'll show you an example in one slide. You're not really sure why it's crashing. You're getting a segmentation fault or a memory violation or a floating point exception or something, and so let me put a print statement in there, or a cout statement. Oh, let's see, okay, got that far, I don't know where else. Print these couts, and I'll remember my good binary searches. I'll put a cout statement every 10 lines or something. Try to figure out where it is. And you can do, yeah, you guys have done that, yeah. I still do that sometimes, depending on the program. But if it's a simple problem, it's a whole lot easier to just run into the debugger and wait till it crashes and say, where are you? And it will tell you, and it's a whole lot faster. So let's see here. Just a couple more things before we do examples. You can redirect input and output from inside the debugger. Redirect input. I can even type the output through more if there's a whole lot. Not typically useful, but since it's in here, I'll go ahead and put it. So let's see if we can switch to an example. So I have in here a really useful program that I have cryptically referred to as core dump. Let's see, can you see that? Yeah, it'll work. All right, so I wrote this. I spent thousands of dollars and I generated this program. And I'm going to run it. Now, the interesting thing about this program is it's designed to tell you the meaning of life, which is something I've been trying to figure out for a long time. So you can imagine that this was a difficult program to write. So I'm going to run it. /core dump, we all know what that means. And oh no, floating point exception. I guess I'm not going to figure out what the meaning of life is. That's really a drag. So let's find out what happened to this program. So I'm going to fire up my debugger. I'm going to say run the debugger on file core dump. That's going to give me a little bit of information about what libraries it's loading and stuff like that. And I'm just going to say run. Okay. So starting program, told you what it did, it read all the libraries. I got an arithmetic exception. I'm starting to get an idea what might be going on here. Now, at this point, it says I'm on line 13. This is line 13 in my program. Now, the most important thing to remember about GDB is when it shows you a line, it hasn't run it yet. So this is the line it's trying to do. Now I look at that and say, well, the result is the top divided by the bottom. Gee, what was in that program? Well, I'm going to say list. Let's start back at the beginning here. I've got top numbers, I've got bottom numbers. Where was I? Line 13. So line 13 says result equals top divided by bottom. Well, I wonder why that would cause a problem. Print top. Top is 42. If you're a good science geek, you know we're actually getting pretty close to an answer here. I don't see anything wrong with 42. What's the bottom? Oops. Yeah, I know. Bottom is 0. Huh. Closing in on an answer right now. So I've got a division by 0 error there. Now, if any of you are curious, it's actually really hard to generate a program that's only 10 lines long that will divide by 0 because compilers are just too smart. So if you're at all curious why the program is written that way, if I had just said print 42 divided by 0 or something, the compiler would say, I'm not going to do that. I know that's going to be an error. So I have to work a little bit harder. So from in here now, I've got an idea that the program died on this line, and it never got this far. Well, what could I do at this point? Well, let's see, print top, that was okay, print bottom. I wonder what would happen if bottom was 1 instead. Huh, okay, so you'll notice that not only can I find out what the program is doing, but I can change variables. So at the point at which I said print bottom equals 1, which is the same as set bottom equals 1, but remember, this program is written by geeky people, and if I had typed